everyone, and thank you for coming to Renew Rebuild Hawaii. We're a town meeting on energy throughout Hawaii and the Pacific. We now have participants from New Zealand and Korea and on every island. So thank you very much for coming. Today, we're going to be talking to Stephen Wells, the new Deputy Director of Hawaii State Energy Office. And Stephen represents a new generation of energy planner for Hawaii. So we're very pleased to have him. Peter Sternlicht from Sustainable Energy Hawaii, Dan Gowin, one of the nation's foremost geothermal experts. I want to thank also our sponsor, Hawaii State Energy Office and Hawaiian Electric, for making this possible, and for Hawaii Pacific University, HPU, for providing us with our very capable intern, Olivia Cropper. Olivia?
Hello, aloha everyone. Like you said, I'm Olivia Cropper. I'm a senior over at Hawaii Pacific University and an intern here at Renew Rebuild Hawaii. And we put together a great program for you guys today. So welcome. We're so happy to have all of our speakers with us. And if anyone would like to volunteer or provide some input in the future about the kinds of things we do here, we would greatly appreciate it. You can just send that to renewrebuildhawaii@gmail.com if you have any thoughts. A few ground rules before we get started. We want everyone to feel like they're able to participate and share their thoughts. So if you have any questions or comments, leave them in the chat throughout the presentations, along with the name of the person that you're asking that question or making that comment to. And we will get to them after the presenters are done with their presentations. So with that, I'm going to pass it over to Stan, who is our moderator this morning.
Morning, everyone. Thanks for joining us. I am also a senior, but I'm a senior citizen. I'm not a senior at HPU. And I'm going to be your host today and moderating. And one other administrative thing, and I see most people are muted. Please mute so that we don't get like my rooster and my dog barking in the background. I'll even be muted when I'm not presenting. So thank you for doing that. So today we have I think a great lineup. We only have 3 presenters, one like Michael said from the state, one that's going to talk about something that's really important, but I think a lot of the people in Hawaii don't appreciate it, and that's called supply chain. And Peter, who lives on the Big Island, is going to be talking a little bit about the bigger impact of energy, and one of them is supply chain. If you remember, if you lived back in the 70s, during the oil embargo, Hawaii was severely impacted by the fact that we couldn't get gasoline, we couldn't get oil, and we couldn't get supplies coming in. But most people weren't living around in the 70s, except old people like me and Michael. So we don't have that vision in front of us very clearly, but I remember it pretty vividly, along with the price of $1 a gallon gas, which we all know is a fantasy right now. But the reality can still hit. And Hawaii is very vulnerable to supply chain issues, and supply chain issues are directly related to energy. So that's going to be kind of the focus as we move forward towards 2046. How are we going to make sure that along the way, we don't make ourselves vulnerable to supply chain issues? So to start off today's discussion, we have Stephen Wells, who's relatively new to the State Energy Office and brings a kind of a new picture. He'll probably tell us how long he's been in the State Energy Office, but he's definitely not an old timer there, as Mark Glick is. But he's got some great insight that he brings with him, along with his youth, to talk to us about how Hawaii's going to be moving forward. And from the time in about 2008, when we started developing the Renewable Portfolio Standard, until it was implemented in the 2015-2016 legislature, to how we're actually going to get there. Every good plan has to be able to adjust and make changes along the way to make sure you can get to your end state. And so Stephen hopefully will be able to talk to us a little bit about where we are and where we're going towards that renewable portfolio standard, not only for the grid, which is what's in the statute, but also for transportation. So Stephen, welcome this morning, and it's all yours.
Thank you, Stan. I appreciate that. And it's very nice to be here today and join a distinguished panel and speak with an audience with such a depth and breadth of energy expertise. I see some familiar names and faces here today and a bunch of new ones. So for those of you that I've met before, hello again. It's nice to see you here. For the new folks, I'm Stephen. I've been with the State Energy Office since about since June, so relatively new. And thank you, Henry, for a fact check on the date for the RPS. So so I'm pretty new to the Energy Office. Before the Energy Office, I was with the Natural Resources Defense Council. I spent some time at the Federal Energy Regulatory Commission, and I spent about a decade at the U.S. Department of Energy, where I got to meet some of the people here, and I got to work on the Hawaii Clean Energy Initiative, which dates back to 2008, 2009, which was a partnership between the US DOE, the State Energy Office, and a bunch of stakeholders in the state, trying to think through what the RPS, the 70% clean energy goal, would look like at the time. And as we all know, that's now been pushed to 100 for the electricity sector, as well as net zero by 2045. So it's quite an ambitious goal, and I'm excited to be able to talk to you all and get some insights from the group here today about what they think works. As you all know, we're in 2023. It's the end of 2023, but it's still 2023. So we've got 21 years, which is in some ways a really long time, but in other ways it's not. 21 years ago, Stan pointed out, there was still $1 a gallon gas. Things can change a lot in 20 years, and it's hard to predict exactly what that's going to look like. There's been a planning effort that I'm sure most of you know about and have read every single line of, just like I have, from HECO and the integrated grid plan that they've produced. And they focus on the electricity sector, and they really try to focus in on what's commercially available today and what does a portfolio look like based on today's commercial technology. And that's a legitimate, valid exercise for them to look at. We right now are going through a similar exercise, but looking economy-wide at net zero by 2045. That report is due to the legislature by the beginning of session. We've done a little bit of outreach about that. It's still in process. We're waiting on some modeling results. We're in the thick of it right now as far as writing that particular report. On our website, there's a decarbonization page. There's a link where you can submit your insights to us. We will read what you submit, and like I said, we're in the thick of writing it right now. So if there is something you want to see us address in the report, definitely go to the website. It's a pretty simple form to fill out. Once I'm done speaking, I'll drop the link in the chat to make it easier on everyone. But now's a good time for everyone on the call to share their opinion with us in that way. So as we think through what 2045 looks like, I think, like, you all have read the IGP and looked at that report, there's a big emphasis on solar and wind. And given the questions that HECO asked, I believe that's appropriate focus. As most of you know, sometimes the sun doesn't shine, sometimes the wind doesn't blow, and what do we do in those circumstances? And there's a few different ways we can approach that. I think for me, what I would really like to see, and we are proposing a bill on this, is really finding out what geothermal resources we have. I think we've got some geothermal experts on the call. They know a lot more about the details of this than I do, but geothermal is sort of like you have to see it to believe it. We don't know what's there until we actually get down there and figure out and see it. So what we want to do is start a statewide slim hole resource characterization program, working with the university. And what we would do is try to find fresh water, hot water, and place this to sequester carbon. It's the same technology to do all of that. It's a 6-inch hole that gets drilled, goes fairly deep. It allows us to get a really good sense of what water and sequestration resources we have below the surface. And until we do that, we just don't know what geothermal resource we have. So we also don't know what carbon sequestration resource we have. And we might find some fresh water, which as you all know, is an important resource to find. So that's one of the bills we're proposing for the upcoming session. Most of you know geothermal exploration and carbon sequestration exploration, anything below the surface is expensive to do. So it's hopefully a start, but it would give us some leverage in talking to the federal government about getting additional resources to do that. We have some conversations in the works with some of my former colleagues at the U.S. Department of Energy to see what might work. But I think that's a really big issue for us, is just understanding better what resource we actually have, so that we can plan accurately based on the data that we have. The university and Nicole and others have done a fantastic job with what they've been able to do so far, and I think we just need to take the next step and get down there and find out what's going on. So that's one of our bills for the next session. We want to take another serious look at pumped storage hydro on other islands. As you all know, KIUC is pursuing a project on Kauai, and we have a report from the Army Corps in 2011. There's also an old, not that old, I guess, but U.S. Department of Energy and DBET report from 1981, looking at the different pumped storage hydro resources across the state. And I think we need to take the next step on that one as well. Some of the work that we've seen, in a heavy portfolio that's really leaning on solar and wind, it works well in most circumstances, but there are periods of time, especially there's like the week of no wind and no sun that most of the folks on the call remember. A diversity of resources will help us get through a period like that without severe curtailment or blackouts. Pumped storage hydro could be a big piece of that. And so what we want to do is really understand what resources out there. We've got some foundational reports. We just need to take the next steps and start to develop some of that capability. And the other big bill that we're going to propose is a biofuels pilot that would look at biofuel crops on brownfields, land that needs to be remediated. So for those of you that want to Google it, it's called phytoremediation. There's been some experience with that in the state as well. I know PAR has looked into it. We just want to encourage that and keep that moving. Because as Stan mentioned, renewable electricity is a piece of it, but transportation is the bigger piece of our energy picture right now. And to decarbonize that sector, we're going to have to think really hard about what's out there and what resources we have. Biofuels can be a piece of that. The land use intensity of biofuels is really high. So I'm not sure how much and at what cost. We can produce biofuels locally, but we want to figure that out with some specificity and understand that really well. So those are the three bills we've got proposed for the session. The session's going to be kind of interesting. Not really sure what to expect on the energy side. So I'd love to hear from the group about that. But one of the other things, in addition to the bills that we have proposed, I also just want to shout out some of the recent successes we've had. Some of you probably saw last week, the U.S. Department of Energy announced that Hawaii was selected for 2 grid resilience grants, and that's the State Energy Office partnered with KIUC to really move the needle on what can be done with grid forming inverters and synchronous condensers. And so those 2 projects, taken together with Kauai's effort on pumped storage hydro, will help Kauai reach 100% clean energy in an accelerated manner. And if anyone wants to talk about grid forming inverters, I'm happy to do that. I know I know enough to sound smart at a cocktail party, but I don't want to bore everyone if that's not of interest. So I leave that out there, and maybe we can get some questions in the chat. As I'm looking at the chat now, before I turn it back to Stan, I want to see, are there any current projects for wave energy? I think most of you know about the test site over on Kaneohe. US DOE is still pursuing and testing wave energy technology here. We're still waiting to get the right one, just one that actually works here. So that would be great. And exactly, James has that answer there. And we got a question from Stephen on green hydrogen for transportation. I think that's a really cool idea. In order to make green hydrogen, you need green electricity. And we don't currently have enough green electricity to meet the RPS. So there isn't enough green electricity to also make green hydrogen. If we find a really rich geothermal resource somewhere, then maybe we're making that hydrogen here, and that could be a really interesting puzzle piece for that 2045 picture. But in order to do that, we need to understand whether and where our geothermal is. So that's kind of the step and why we've got that priority bill. I see OTEC. OTEC still is one of those technologies that's like 20 years away every year. So we can come back to OTEC and Veronica's question about marine and aviation decarbonization beyond SAF. I think there's some interesting electrification options, especially for inter-island. There isn't, in my research on looking at electrified marine and aviation, it's not quite clear when that's going to be commercialized and something that can be deployed for the long haul stuff. But there are some interesting electric options for shorter distance. So we'll want to explore that as well going forward. So I'll stop there and turn it back to Stan.
All right. Thank you very much, Stephen. We appreciate your insight, and thanks for the positives on geothermal, because that's kind of where we're heading in most of these discussions today. Our next speaker up is Peter Sternlicht from Sustainable Energy Hawaii. And for full disclosure, I'm also on the board of directors of Sustainable Energy Hawaii, so we don't mean to double team everybody, but Peter is a great communicator, does movie productions, and is just an incredible illustrator / digital illustrator and communicator, and has done some great work. If you can look up online some of his documentaries on energy, you'd be really impressed. So we're lucky to have him. He lives on the Big Island, and he takes the whole topic of sustainable energy very seriously. So Peter, I turn it over to you.
Thanks, Dan. Yeah, it's pretty important. It's actually why, I mean, it's a big part of why I moved to Hawaii, because, I've been studying this subject for quite some time, and in particular petroleum. And, things are changing, and I don't, maybe I should just dive into my presentation, and I think it'll all make sense. By the way, I'm packing a lot into this, so I'm going to be reading what I have here, so bear with if you don't mind. All right, so let me see here. From my perspective, today's topic, decarbonization or energy transition, brings up a host of related topics I don't really hear being discussed publicly or detailed in our energy policy. It's clear there's a consensus surrounding the climate debate that finally has governments and businesses taking action. That consensus includes targeting the burning of fossil fuels as the main cause, and also naming carbon dioxide as the biggest culprit. The goal of reducing carbon emissions is widely referred to as decarbonization. After all the discussions about semantics or terminology, I think the way we're going to mitigate climate change is to electrify the global economy. And of course, transitioning away from fossil fuels to renewable power is how we plan to get there. It's important to understand that by electrifying the global economy, we'll be transforming modern life into something very different than what we experience today. The energy systems we want to replace are currently ubiquitous around the world. To be successful at this scale, it makes sense to do so with a coordinated global response. However, what we see happening is that pretty much every city, state, county, and nation is crafting their own plans. Those able to transition at a massive scale will likely set the standard for the rest of the world. At the same time, the exponential demand they place on the global supply chain may impact smaller economies' access. At SEH, we believe assessing what the rest of the world is doing needs to be part of the conversation as we prioritize our electrification strategy here at home. My goal is to illustrate why electrifying even a small economy like Hawaii's suggests including metrics beyond carbon emissions and the speed at which we transition. To begin with, we know the Hawaiian Islands are the most remote inhabited location on the planet and small by any standard. We also know that Hawaii is dependent on the rest of the world for 90% of what keeps its economy running. History has shown that institutional change here is a very slow process. That makes the task of expanding our own clean energy goals quite challenging. This last point leads me to ask a few questions. Are Hawaii's energy policies in sync with those being implemented around the world? Are they flexible enough to support the development of an entirely new energy landscape and do it with the urgency required by law? Can we execute this energy transition and sustain a local economy that investors expect to keep growing? So speaking of the economy, maybe we should define what an economy is. It's important to understand that within any economy, energy is the master resource. It's also important to understand that while energy can't be created or destroyed, it is constantly being converted from one form to another. Physicist and economist Robert Ayers described the essence of an economy like this. An economy is a system that extracts, processes, and transforms this master resource, energy, into products and services. That means nothing gets done in an economy without consuming energy at every step along the line. The graph you see here plots 50 years of global energy consumption against its corresponding GDP. The correlation variation between the two is less than 1%. Given this, it's reasonable to conclude that economic performance directly corresponds to the energy consumed by it. Energy is the input, the value of the economy is the output. Therefore, if an economy consumes more energy, it tends to grow. Conversely, it's reasonable for the opposite to be true too. As we dive further into this presentation, I think this is an important connection to keep in mind, especially if our plan is to replace where much of that energy comes from in a little more than 20 years. So the big question is, can intermittent wind, solar, and battery systems we see being deployed at an exponential rate deliver enough power to meet our existing needs, as well as to deliver the power we know will be needed to electrify light-duty transportation, industrial transportation, and the heat-intensive industries like steel, cement, petrochemical refining, and food processing? Our energy reality is this. Modern civilization exists as a continuous economic activity, and the flow of energy is how and why. Right now, 3/4 of the global economy's energy is derived from fossil fuels. And among those fossil fuels, the liquid fuels that serve as the lifeblood of modern just-in-time logistics has no replacement at scale, nor is there one on the horizon. For me, seeing the scale of these logistics is really a stunning experience. This is a snapshot of maritime traffic moving the global economy from one end of the planet to the other. This is another snapshot, but this time it's global air traffic. It's the norm to find 20,000 commercial aircraft in the air at any one time and average more than 100,000 flights a day. In July of this year, we saw more than 134,000 flights set a new single-day record. But wait, there's more. Those numbers don't include military, private, or cargo flights. Again, all of these are powered by liquid fossil fuels. This is what the global rail system looks like. The freight market grew by 5.6% in 2022 and is forecast to continue growing at a rate of 5% per year through 2027. In total, 95% of global transportation energy comes from liquid fossil fuels. We hear a lot about what electrifying light-duty transportation will do to reduce emissions. Progress in that direction is really just getting started. In 2021, less than 1% of light-duty vehicles in the US were fully electric. That's definitely changing, though. EV sales grew in the same period to 5% of all new car sales and had grown to nearly 7% of total market share by January of this year. Combined, light-duty vehicle sales were either hybrid, plug-in hybrid, or electric. Even with this growth, the EIA still projects less than 10% of the total light-duty fleet will be EV or PHEV by 2035. Today, with virtually all transportation powered by liquid fossil fuels, maintaining our current economic activity and decarbonizing at the same time means replacing that energy with portable fuels that start out as clean electricity. That will require, this is on a global basis, by the way, this will require terawatts of renewable power on top of what's needed to replace the non-renewable power we use today. The leading candidate to serve as the building block for these carbon-free liquids is electrolyzed hydrogen. But it's not just making the hydrogen or generating the initial power to produce it. It also means producing an entirely new interconnected distribution network while keeping our existing system functional as we build its replacement. So now, having a more detailed sense of the task at hand, let's ask this question again. Can the world achieve meaningful decarbonization at the same time it constructs a replacement for the existing fossil fuel system and keep the global economy running at speed too? To help answer that question, let's take a look at some more data. Our World in Data, the publisher of this graph, plotted energy consumption by type over the past 223 years. For fossil fuels, they have data for oil, coal, and natural gas. And for renewables, we have hydro, nuclear, wind, solar, biomass, biofuels, and other low to no carbon sources used to generate electricity. One thing that stood out to me was the exponential growth in fossil fuel use that's taken place since World War II, and that the adoption of modern renewables like wind, solar, and biofuels didn't really start to register until around 2005. With decarbonization becoming the primary focus for mitigating climate change, I wondered how much progress we'd made since 2000, a date prior to any real effort towards addressing climate change got going. From the data in this chart, I was able to create this spreadsheet comparison. So what I did was to look at the relationship between fossil and non-fossil fuel consumption in our total energy mix. First, I looked at their combined annual consumption in 2000. From there, I did some simple math and calculated the ratio between the two categories. I came up with 77% fossil and 23% non-fossil. Then I did the same for 2022. I was really shocked to see that the ratio was identical 23 years later. It hadn't even changed by 1% in more than 2 decades. Now, I immediately contacted my colleague who works for the Hawaii Natural Energy Institute and asked him to check my math. He got the same thing, so I felt a little bit better. So looking at more of the detail, I saw that there had been a 110,000% increase in solar deployment and a 58-fold increase in wind. Even with that exponential growth, solar's overall contribution to the energy mix was less than 2%. And with both solar and wind combined, it tallied up to just 5%. What will it take to achieve 20 or 25%? And again, this is on a global basis. Another striking observation was the overall increase in consumption over that period, 46% in 23 years. What's clear is that as of 11 months ago, the global economy isn't burning fewer fossil fuels. In fact, with that kind of increase, we're emitting more carbon than ever. This graph illustrates the measurable change in atmospheric CO2 concentration between mid-January of 79 and mid-January of this year. Nowhere do we see even a plateau, much less a decline. Seeing this trend and understanding the emissions goals Hawaii has set for itself, I wanted to ballpark what its proportional contribution to global emissions pencils out to. Data published in 22 for 2019 showed that Hawaii's petroleum consumption was slightly more than 47 million barrels that year. By comparison, global consumption for the same time frame was about 36 billion barrels, or around 100 million barrels each day. That means over the course of 2019, the oil Hawaii consumed was approximately what the world consumed in little more than 11 hours. For the purposes of this discussion, a reasonable conclusion would be that carbon emissions would track in similar proportions. Out of that oil consumption, about a third of it was used for power generation, meaning a year's worth of Hawaii's grid power emissions was produced by about 16 million barrels of oil products. That approximates what the world emits in about 3 hours and 45 minutes. And I don't mean this comparison to be rhetorical. While it may seem simplistic to some, I still see this kind of comparison being relevant, and I'll illustrate why as I continue. Looking at the implications that come with this analysis, quite a few questions come to mind. For example, given the urgency to combat climate change, why is the world consuming more and more fossil fuels? It's not like governments around the world don't understand the predicament we face. When I think about it, I'm pretty sure that within our economic system, those who invest in it and govern it believe growth is essential. And without that growth, their venture is failing. As we've seen, growth always involves increased energy consumption. What else are they going to use? Okay, so hypothetically, let's take the predicament of climate change to an extreme and imagine what would happen if the world stopped consuming fossil fuels today. I see reports where thousands and thousands of people would say, do it in a heartbeat. Obviously, we're not going to do that. However, it does open up the possibility that if the world doesn't decarbonize at the same rate Hawaii does, and knowing we're not able to move the climate needle on our own, maybe we have the flexibility to consider things like long-term systems resilience or economy-related opportunities as potential outcome goals. For example, it might make sense to model the scale a distributed intermittent system would need to achieve to replace all our grid power and on each island. How much power would we need to produce the volume of clean liquid fuels we forecast? And how do we do that within varying economic scenarios like domestic-only production or export scale production? Maybe we could also compare firm baseload power generation systems and their life expectancy with those of intermittent systems. We know the capacity factor, flow rate, and footprint issues fare far better with these systems than with intermittent. Another factor that could be modeled is whether the exponentially growing raw material supply chain for solar, wind, and batteries will remain economically viable when the time comes to replace components like battery backup systems. That could actually begin as soon as the mid to late 30s. And then there's the question that's often overlooked. What if carbon emissions isn't the only reason to electrify the global economy? This question specifically targets the economics surrounding liquid transportation fuels. We know petroleum is a finite resource that appears to be reaching the upper limits of its daily flow rate, especially as we now consume it at a rate of nearly 37 billion barrels each year. The reasons and exact timing of that limit are widely debated. We'll look at the subject in more detail later in the presentation. I think one of the problems surrounding our energy transition is public perception and understanding what renewable energy really is. Most people think that solar and wind farms are renewable energy. The fact is, renewable energy is not the same as the systems used to transform that energy into work. Solar panels are not renewable energy. Wind turbines are not renewable energy. Batteries are not renewable energy. The renewability of systems is not the same as the renewability of their energy inputs. Every system we deploy capable of transforming renewable energy into usable work requires fossil fuels to mine, refine, smelt, manufacture, and to transport around the world. And once again, liquid fossil fuels serve as the critical link in that supply chain. It bears repeating, there simply is no replacement for petroleum at an industrial scale, nor is there one in sight. Let's consider today's renewable energy system supply chain. If we accept that petroleum is part of every process, it's important to remember that the supply chain for every renewable energy system starts with mining. In recent years, we've seen supply chain issues blamed for countless delays in delivering products the market wants. These are some recent headlines reporting supply chain challenges. They range from cost issues to geopolitics to materials shortages. What can we expect from the renewable energy supply chain going forward? Is there a backup plan if mining and refining and manufacturing systems can't meet the demands of our climate goals? As the world transitions from fossil fuels to renewably generated electricity, how confident are we that upstream systems production can reliably keep pace with the exponential demand growth? This graphic illustrates the growth rate CRM mining needs to achieve to meet 2050 climate targets. As you can see, the steepest slope in the curve occurs within the next 5 to 10 years. What follows will illustrate one of mining's biggest challenges. Here we see a list of where all the critical raw materials needed to manufacture solar panels and wind turbines and batteries originate. One thing that stands out to me is how many of those materials considered critical are mined within China's borders. When considering geopolitics and China's influence over CRM, we have to remember that in addition to their own resources, China's been buying up rare earth mining rights across Africa, including Guinea, Zambia, South Africa, Zimbabwe, and the Congo. China also produces about 80% of the world's gallium and about 60% of the world's germanium, materials that are critical to the manufacture of semiconductors. Once materials have been mined, they still need to be processed and refined to satisfy varying degrees of purity. After processing, they're transported and made into components, transported again, or they're ultimately integrated into larger, more complex systems, which are then transported again. As we can see, China again dominates CRM processing for both renewable energy systems and EVs. They also command a significant portion of components manufacturing and systems integration. I think it's fair to say at this point, most of the world is looking at solar voltaic systems to generate its clean electrical power. Solar-grade polysilicon is the primary material that enables these systems to generate power. Today, 75% of the world's processed polysilicon comes from China, as do 80% of the completed panels. These systems are increasingly being deployed along with grid-scale battery backup systems. Again, these backup systems use many of the same raw materials as EVs. The IEA forecasts the existing global EV fleet of approximately 26 million vehicles will more than double to 60 million by 2026. SEH has a working relationship with a research scientist, Dr. Simon Michaud. With his PhD in mining and natural resources, he's been exploring just these kinds of scenarios at the Geological Survey of Finland, also known as GTK. The data you see here is part of his work GTK has been publishing. What's shown here represents estimates for the quantities of selected high-demand CRMs needed to produce one global-scale deployment of renewable energy systems capable of phasing out the use of fossil fuels. Its scope is based on raw materials component data present across today's functional, scalable, renewable power generation and storage systems. This is an exercise to establish the magnitude of what electrifying the global economy will require in terms of natural resources. As you can see, the metals selected are listed on the left, with estimated task-specific quantities for each. Those estimates are based on current fossil fuel energy consumption data, and then are converted to give us the renewable system equivalents needed to produce the same usable energy. These calculations include efficiency gains that arise when using electricity versus combustible fossil fuels to deliver the same usable work. The quantities listed in the first column is the volume of metals required to produce that one single generation of renewable energy systems. The center column of numbers represents the known volume of global reserves that are yet to be mined as of 2022. The column to the far right is the ratio between what's needed and what's available. Even if these numbers are off by a factor of 500%, generating enough renewable energy to maintain the existing global economic output without using fossil fuels seems unlikely. Keep in mind that this scenario only produces one generation of renewable energy systems. All these systems will need to be replaced on a regular basis. Even with expanding mine development investment, historically for every 1,000 mineral deposits discovered, only one or two become mines. The time taken to develop a discovered deposit into an operational mine takes about 20 years. Then there are the economics in mining ventures. For every 10 producing mines, 2 or 3 will either lose money or shut down. As we discussed earlier, there's the critical matter of the liquid fossil fuels we use to move the global economy from place to place. Among them, rail is currently the most electrified mode of transportation. According to the IEA, 45% of rail transport was powered by electricity in 2022, making it the easiest mode of transportation to decarbonize further. Maritime shipping and commercial aviation will be significantly more difficult to electrify. Again, hydrogen is the prime candidate from which to produce clean, liquid transportation fuels. Challenges there include how to reliably source the volume of clean electricity needed, and critically, the equipment that can use these new fuels. Those haven't been built yet. Each year, Rystad Energy, a well-respected global energy analytical company based in Norway, consolidates the data published by the IEA, the EIA, and the BP Statistical Review, and then issues their own assessment. In each of the last 2 years, the data showed that recoverable oil reserves contracted by 9% year over year. That's not what was consumed. It's what remains to be extracted within economically viable parameters. They go further to suggest that by 2050, the daily flow rate of oil will be half of what it is today. They also offer an upside, which is by burning half of what we do today, carbon emissions will be significantly reduced. If accurate, that will also impact the size of the global economy. JP Morgan Commodities foresees a similar trend as Rystad does. As you can see, they illustrate that within the widening gap between the black demand line at the top and the flow rate bands below, if history holds true to form, which Morgan seems to believe is the case, the impacts of what we've termed a supply deficit will likely be felt across the wider global economy with higher costs. In conclusion, it's not hard to see a similarity between energy consumption GDP and the atmospheric CO2 trend lines we saw earlier. As we pursue climate mitigation strategies, it seems reasonable to accept that energy, the economy, and the emissions that come from them have maintained a clear direct correlation to one another through the last half century. What I see baked into this data is a world that's in a predicament, and predicaments have outcomes. Those outcomes will likely change life as we've come to know it, versus this just being a problem we'll be able to fix. How we adapt to this predicament will be a defining factor for all who live here. When it comes to the future of energy, Hawaii is blessed. We have options most of the world does not. We can make decisions that might help us minimize the undeniable impacts of climate change, diminishing natural resources, and what looks like an inevitable economic contraction. We have the option to develop baseload power systems from geothermal heat, an indigenous resource that can deliver a lot of power. In doing so, we might be able to transition from a tourism and military-based economy to one capable of exporting clean energy to part of the world that faces much greater challenges than we do. Making these decisions will not be easy. They will be controversial, and time to make them is not on our side. Whatever we would do will require some well-informed, honest, and determined leadership. Mahalo.
Peter, thank you. Now you see why I pick folks like Peter to be people I want to associate with, because they're a lot smarter than me.
No.
But, I want to point out a couple of things that Peter brought up in his presentation, and I've kind of picked up some of the stuff from chat too. The part about China controlling so much of the rare earths and materials that we need to move forward with technology brings up the point of our current relationships in the Pacific vis-a-vis China and Taiwan being strained right now. And the chip shortage that affected our automobile production not so long ago, just a couple of months ago, was directly related to just what Peter brought up, the supply chain and the power that China has over much of the supply chain and critical elements that we need. So we need to be paying attention to our global political endeavors as a nation with China and other countries. Another thing that I saw coming up in the chat was biofuel. And the one caution I would use is that we went through this with ethanol. When you start using food things like corn and stuff to make fuels, you also impact the food chain and the availability of food. So if we do look at biofuels, I hope we're looking at byproducts of food like corn stalks instead of corn, and other leaf substances and things that we can do biofuels from. And also, like I'm sure you'll hear more, Peter mentioned it, but more from Dan, is using hydrogen to make liquid fuels, which is a chemical process which is already proven. Another thing of concern, and I think a big concern here in Hawaii, is when we do geothermal, we have to concern ourselves with the potential for contaminating our freshwater resources. And that's certainly something we need to watch and be concerned about, with the Navy's issues at Red Hill being not too far in our rearview mirror and still impacting us today. We need to treasure our freshwater resources. And if we're going to do geothermal, we have to understand the risks and also ensure that our systems that we use don't contaminate what freshwater resources we have. Another point on that same line is that salt water can be used for electrolyzing hydrogen. And I think we have quite a bit of salt water in the neighborhood. So I would consider that as an option for electrolysis instead of tapping into fresh water. With that little piece of trying to catch up on some of the Q&A, and some of the things like wave energy were addressed in the chat, I'll turn it over to Dan for his presentation. And while he's setting it up and getting his slides set up, I'll just add that Hawaii is in a unique place. We are in the middle of the ocean. I call our 2,500-mile moat, but salt air is very hard on ocean-based things like wind turbines, like wave machines. The wave energy projects that have been done off of Kaneohe Marine Corps Base, Hawaii, have proven to be very maintenance intensive and a tough challenge. But then there's also the potential for undersea turbines that don't go off of waves, which are intermittent and wind powered, but go off of sea currents, which are powered by the moon and tide changes, and are a possibility that Dan has actually looked into, and we've done some presentations on that. So, Dan, over to you.
Thank you, sir. So my name is Dan Gowin. For those of you who don't know who I am, giving a rundown of my family history, and it really is a lot of family history. Most of my family is nuclear Navy, so I've grown up most of my life either in the military sphere or working in government labs. Most of my family ended up working at the Idaho National Engineering Lab, so I've got a good background in nuclear power. I've also got some family members that work in the oil and gas business, like over the state of Wyoming. Whenever I spent most of the 80s in the United States military, by 1990, I was working at the Crane Naval Service. Excuse me, just a minute here. Working at the Crane Naval Surface Warfare Center in southern Indiana. I ran JDAM, Tomahawk, and Trident. I ran the Tomahawk cruise missile for 6 years. Whenever I left the Department of the Navy, I went to work for Indianapolis Power and Light. My mission there was to automate everything that was bolted down in all the way from coal-fired power plants to grid control systems, all the way down to the maintenance system that linemen use for maintaining the power grid there in Indianapolis. From there, I went to a place called Mid-Continent ISO, known as MISO. I'm the guy that designed the computer system that controls the power grid for 26 states and parts of Canada. And for those of you who may ask this, I am one of the survivors of the 2008 Eastern Power Grid blackout, just to let you know that. From MISO, from that system, I ended up at General Electric at their alternative fuels program. When I first arrived, the CF6 jet engine could only burn jet fuel. By the time I left, it could burn 22 fuels, and I'd already converted 4 coal-fired power plants over to gas turbine. From there, I was at Eli Lilly. I ran payroll and the financial system at Eli Lilly for 8 years. After that, I was asked to basically get into the energy sphere because of a lot of the pressing energy problems that we're having. That was in 2013. That's when it was becoming apparent that looking at 10, 20 years, that the supply of fossil fuels was going to become ever more problematic and probably cause a lot more issues than what things were being solved. Let's see here. Okay, so the first part of the presentation starts off with this slide here from a good friend of mine, the Station Murkowski over at the Department of Energy. He runs the nuclear power over there. And that has to do with when it comes to grid power, there are 2 very important things. One is the capacity factor. The other one is how much does it cost per megawatt hour. In this slide I'm showing you, it's from the year 2020. You can look up the top where your base load, that's your what we call base load. Your most reliable power is up the top, and then the least desirable power you have is down at the bottom, and it has to do with how intermittent the power is. And as you can see the slide right there, the 2 most reliable energy sources we have is actually nuclear and geothermal. Even though this slide points at the old geothermal, there's been some advancements in geothermal that actually brought nuclear power and geothermal up to on the same bar. Okay. This here is the Raft River binary geothermal power plant. How this power plant got started out is back in 1971. Actually, a relative of mine went out there and drilled a water well for a rancher and what happened was he hit hot water. By the 1970s, we had a pretty serious energy crisis. The Department of Energy was able to get some research money, and my dad and a bunch of his submarine friends built this binary geothermal power plant. This binary geothermal power plant is very different from the other types of geothermal power plants, and we're going to go into all the things that make this power plant different. The The Raft River Power Plant was brought online in 1980. Originally, it was outfitted with a Westinghouse 140 megawatt steam turbine. That steam turbine, they used that turbine all the way up to the year 2000. The year 2000, Ormat bought the power plant. They removed the Westinghouse turbine and replaced it with an Ormat turbine that only produces about 20 megawatts worth of power. Okay. So the binary geothermal power plant has some differences to the other original geothermal power plants, and the reason why I said this: the original plants, what they took is they took live steam. They used live steam to drive the turbine. What you see right before you is one of these 110 megawatt steam turbine. The problems with using water directly from a geothermal well, number one is you have a lot of minerals that are dissolved in the water, and when they come in contact, and as the steam expands inside this turbine, it tends to lay those minerals down on the blades. The other downside of using water for a steam turbine, understand the metals in this turbine, it's made out of stainless steel, but even after 10 years, you can see the corrosion that water is causing on the turbine. So there's one problem that you have with using water, or even using water directly out of geothermal, or even if you're using, like say, a coal-fired power plant or even a nuclear-fired power plant, is going to have the same corrosive effect on your turbine. Okay. So there's one problem. The second issue has to do with what you're seeing here. And let me see if I can move this down a little bit here. Okay, so what this has to do with what we call supercritical steam. In order to use steam to drive a turbine, you have to drive the temperature of the steam up to 705 degrees or 374 degrees Celsius. The only downside is that the maximum technical drilling temperature is 482 degrees Fahrenheit or 250 degrees Celsius. I think Baker Hughes is able to get up to 300 degrees Celsius, but the point being is we're not able to drill deep enough to get the temperatures up to actually bring steam up to a supercritical temperature to drive a steam turbine directly. Now, there actually is a solution to both those problems, and I'll show you what they came up with the Raft River Power Plant. Inside the binary geothermal power plant. What they did is they took the primary fluid coming out of the ground and they put that in a closed loop, and they ran that water through what's called a heat exchanger. And I've got a diagram. I'll show you what it looks like later on. And what they actually used to drive the turbine is a fluid called pentane. Now, believe it or not, most of you have actually been exposed to this fluid called pentane. About 20 to 30% of gasoline is pentane. They take a lot of different things to blend together to make gasoline. One of them has to be pentane. Well, pentane goes to a supercritical state at 196 degrees Celsius or 385 degrees Fahrenheit. What that also indicates is you don't have to drill geothermal wells as deep as what you would have to do with steam. So what I'm trying to tell you, currently we don't have the technology to drill wells deep enough for using steam to drive a steam turbine, but we do have the technology to use pentane to drive a steam turbine. When you bring those factors together, you get this here, which is called the binary geothermal power plant. Move this around here. Oh, there we go. Now, basically, remember what I said, that the guys that put this together, a lot of these guys used to run submarines, mainly nuclear-powered submarines. So what you've got here is your primary loop is you're injecting cold water down into the ground. And depending on when you're at will dictate how deep you have to actually drill to make this work. So you got cold, dense water going down in the ground, then the water comes back up in what we call a production well. 440 degrees Fahrenheit is hot enough to do this. Understand that's a complete loop. It's also pressurized. It's pressurized for two different reasons. One is you have to keep the injection well and the production well pressurized to keep the fracture network deep underground, to keep that all pressurized and in place so it doesn't collapse on you. The other reason why you have to keep it pressurized is that pressurization keeps all the minerals dissolved in the water, so you don't have that scaling issue that a lot of the older generation geothermal power plants have. Now, that water circulated through what's called through the vapor generator, which essentially is a heat exchanger. So inside that heat exchanger, that's where the pentane is brought to a boil, brought up to that supercritical state, and you can use that pentane to directly drive your turbine. But the point being here is your turbine, the generator, your transformers, all the things that you attach to the grid. The only thing that's changed essentially is what you're using to drive the turbine, whether it's nuclear powered or whether it's coal fired powered. The point is by switching over to this, you can have a power plant that generates the same amount of power using the same type of equipment you can do the same technology. Now, there's some caveats to this technology. One of them has to do with depth. I think I've got the next one here. Okay, so what is this all based on? Well, it's based off some basic geology of the planet Earth, and that is basically every 2,000 feet you drill down to the crust, the temperature increases by 30 degrees Fahrenheit. The state of California has a geothermal power course that you can take, and according to their course, for every kilometer you drill down in the crust, the temperature increases by 28 degrees Celsius. So the point being is that temperature is proportional to how deep you drill. Now, in the case of this type of power plant, you would not place this power plant in a geologically unstable area. You need a geologically stable area. And the reason why is because you're drilling multiple wells down to form what we call an engineered geothermal system, where you're drilling one well, you're injecting water down in the ground, and then production wells where the water's coming back up, and you're continuously circulating that water back down into the crust. This type of power plant, you could take, for example, a 1 acre plot and drill up to 12 wells off that same 1 acre plot. And that's, let me hear it a second. And this is, and as an example here, this is one of the Hitachi's 110 megawatt turbine plant that I've been running some models on, where I converted it over to a geothermal power plant, and understand that the size of the drill pipe that should be drilling down in the ground is of an 18-inch diameter drill pipe, just like what we did there at Raft River, because the key to this, not only to have hot water come out of the ground, but you want to have a quantity of water coming out of the ground, so you can use that to transfer the heat over to drive the turbine. Okay. Now, what are the economics of this? Well, the Department of Energy, every year they put out a report called the Annual Energy Outlook. The last one I'm showing right here is from 2022. The two columns that are important on this is, on the left-hand side, you have the capacity factor, and the right-hand side, you have the total levelized cost per megawatt hour. Now, if you look here on the left-hand side, you've got ultra supercritical coal, combined cycle, which is your gas turbine, where you converted an old coal-fired power plant. You've added a gas turbine using the exhaust from that gas turbine to drive a boiler, to produce steam, to drive your steam turbine. And then you got your advanced nuclear, which happens to be your small modular reactors, your geothermal, and your biomass. And that, essentially, that's where you're burning wood chips inside of you're converted an old coal-fired power plant over to burning wood chips to basically do the same thing. Now, if you notice here, what's happened is they've upgraded geothermal up to capacity factor of 90%, because the Department of Energy recognized that the binary geothermal power plants are just as reliable. Are just as reliable as the reactors. Now, if you look over on the right-hand side, you'll notice that the costs are quite significant. So an ultra supercritical coal-fired power plant is $79 per megawatt hour. Your combined cycle plants only roll in at about $44 per megawatt hour, mainly because natural gas is currently cheap right now. Of course, in other parts of the world, natural gas is a lot more expensive than what it is here in the United States. And then you got advanced nuclear. It turns into some of the most expensive power, and the reason why is originally, when they were looking at small modular reactors, their costs were coming in about $50 per megawatt hour. What drove the cost up is when you consider, what do you do with spent nuclear fuel? Do you store it? Do you recycle it? So forth. That drives up the cost of nuclear power directly. And that's when you go through the entire complete cost, what it costs you a nuclear power. Then you come to geothermal. If you notice, their geothermal happens to be, when it comes to base load, it happens to be some of the cheapest electric power, period. And next one we roll out, you've got biomass at $86.53. And the reason why that comes in so high mainly has to do with, because you're essentially importing wood. I mean, I know there was a proposal there in Hawaii to use it to like cut down invasive species like trees and so forth, and burn that in the power plant. But eventually you're going to run out of trees in Hawaii, and you're going to be importing like lumber and wood chips and so forth from Canada. And that's what drives up the overall cost. And then after that, you get down to what we call the intermittent power source, and that's onshore wind, offshore wind, your solar hybrid. Some of the most economical power we have there is actually standalone solar. That's the actual solar panels you put on your home. Solar hybrid happens to be solar mixed with batteries. It's not quite as efficient as what just standalone solar is, mainly because our battery recycling technology is not right what it should be. The next one you got down is hydroelectric. And you can see the costs are really rather high there. And of course, the capacity factor is rather surprising for most people. What that has to do with is because you're not able to pull power off of a hydroelectric dam all year round, because there's a certain part of the year where the reservoir actually has to refill with water. So there's only a certain part of the year when you actually drain water out of the reservoir and actually turn that into electricity. Down in the bottom, you've got capacity resource technology. That's your peaker units. One of the things that's happened is that the Department of Energy has recognized that a combustion turbine that's pulling natural gas off of a gas well is actually equivalent to a battery. And the reason why is because, for example, here in Indiana, we pull in the springtime, we pull gas up from Texas, and we store that gas underground in depleted gas wells here in Indiana. And therefore, in those times when we need that energy, we pull that chemical energy, that natural gas, and burn it in a gas turbine. You can start up a gas turbine within 15 minutes. So from that functional standpoint, a peaker unit, a combustion turbine is actually equal to a battery. Now, that combustion turbine does have some advantages over the battery, but they're complementary technologies once you get down to the details of it. One of the more interesting aspects of this is most people are rather surprised. You've got offshore wind there, happens to be some of the most expensive electricity out there. And especially if you look at the capacity factor of only 43%, but yet it's $98.01 per megawatt hour. The reasons for that mainly has to do with salt errors is very corrosive. And if you look at the column, it says levelized fixed operations and maintenance for offshore wind, it happens to be pretty high at $30.58 per megawatt hour. So wind and anything come in contact with the ocean's got to have a lot of high maintenance aspects to it. Okay. What's next one here? What this one here has to do with what we call a value cost. You've invested all this money into a power plant. Let's say it's a coal-fired power plant. You run it for 50 years. After you run it for 50 years, what is the plant worth after you've depleted the plant, after it's used up its useful life here? For example, it's not really that surprising when you look at a coal-fired power plant that's only worth, that the equipment, everything there is probably only worth about 47 cents on the dollar. You get the same problem with nuclear power, mainly because most of the cost of implementing nuclear power is not in the fuel of the reactor. It's really in the building that surrounds the reactor and all the safety equipment. One of the aspects of nuclear power is it does a lot of damage to structures, concrete, steel, so forth. A lot of that equipment after 50 years, you can't reuse it other than you have to jackhammer it up and put it into some kind of a low-level storage location. Now, out of all the power plants there, it's rather surprising. It shows here that a geothermal power plant is actually worth more used than it was brand new. And the reason why is because when you greenfield and you built that power plant to begin with, most of your initial cost was in drilling those wells. Once you drill those wells, they're always going to be there. Excuse me. I'm sorry. Let me drop that down. Sorry about that. I've got a timer on this, so it goes off automatically. Stan gave me a limit how long I can make my presentation, so that's what I'm. So that's one of the aspects of geothermal. That power plant's actually worth more used than it is when you first originally did it. Most of the equipment in the plant is rebuildable. Your steam turbines, gas turbines, all those things are rebuildable. If you notice the combined cycle, which is a gas turbine combined with steam turbines, all that, the reason why that is worth 99 cents on the dollar is because you can rebuild a steam turbine, you can rebuild a gas turbine, and that's one of the advantages with those types of power plants. Now, when you look down at like solar panels and hybrid electrics, mainly, especially your standalone solar panel, say, why is that worth 98 cents on the dollar? Well, that goes back to look at all the precious metals and rare earth elements that were used to construct your solar panel. That's why those have a higher used value. Okay, so the next part of this, and this goes back to some studies that Sandia National Labs, that's part of the Department of Energy, went back and did some studies on. And one of the things that the Department of Energy was rather surprised was that had to do with the United States and our history with hydrogen. One of the aspects when you start looking at hydrogen and the amount of quantities of hydrogen you have to produce to replace fossil fuels, the first thing you run into is as a quantity problem. Is that turns into a storage problem because of volumetrics because you're trying to store a gas. Surprising to a lot of people at the Department of Energy, they found out that the United States has a history with hydrogen dating back all the way to the 1840s, long before the natural gas system was ever installed. What it goes back to is there's an old system called the town gas system, which used something called water gas. What water gas is essentially they would take coal, they put it in a blast furnace, they light this coal on fire, and then they would inject steam into it, and that steam would react with that carbon to form carbon monoxide and hydrogen. 40% carbon monoxide, 6% hydrogen. Surprising to them, they found out that even back then they were having some issues with storing hydrogen because of the volumetrics of the gas. Come to find out, the Department of Energy found out that these towns, when the old town gas system, what they were doing is they were storing the gas underground for a lot of different reasons. One of them has to do with the volumetrics, but the other one had to do with safety. The safest way of storing a lot of gas is underground. Even today, I just described to you how we store natural gas in the natural gas system. We actually pump the gas down into depleted gas wells, and that's where we store the gas. Right. So this document here is they went through and said when they looked at not only how do you store hydrogen underground, but also they did some test case analysis of actual cities and how would you replace the fossil fuel business. When we're talking about replacing diesel and gasoline and transportation fuels. And it just so happens you can also use the same gas for powering the power grid, like in, for example, gas turbines for peaker units and so forth. Right. So what they came up with is that there are actually 4 different geological forms of storage that we've been using here in the United States all across the country, dating all the way back to the 1840s. You got your salt caverns, which is the oil and gas business used extensively. The town gas system, a lot of towns would actually store it underground in aquifers. Here in Indiana and Ohio, they would store a lot of that the carbon monoxide and hydrogen, the water gas, in depleted gas wells. And of course, you got hard rock storage, but that's all been done in minimal amounts, mainly because of cost. Probably the most economical way of storing gases, especially if you don't have a place where you've got depleted gas wells, right? Depleted gas wells is using horizontal drilling and fracking technology where you can build synthetic gas storage facilities. And that's basically an offshoot of the depleted gas reservoir technology. What they came up with starts out with a set of charts, mainly the studies they did for Houston, Detroit, Pittsburgh, and Los Angeles. Now, if you look down there, if you're going to get 100% sizing or basically market penetration, you're going to replace all the diesel and gasoline, let's say in the city of Houston, you would have to be producing 159,292 kilograms of hydrogen in a day. And of course, you would have to store that gas in depleted gas wells. And you would have to have a cushion gas about 19 million kilograms. And of course, you can look at the volumetrics amount of gas. And if you sit down and calculate, say, for example, you're going to use electrolysis, we're using electricity and water to turn water into hydrogen gas. For example, the city of Houston, you would have to have at least 300 megawatts worth of generating capacity for turning water into electricity, for storing that much gas per day. In actuality, you wouldn't go with 300 megawatts strictly. You would probably build 400 megawatts worth of generating capacity to not only the amount of gas that you're putting in storage for backup power for the grid, right? But you would also, like I said, you can use that for providing transportation fuel for that city. If you now notice you've got Pittsburgh is sort of on the low end. Los Angeles is up on the high end. It's almost a gigawatt worth of power. And you got Houston and Detroit are basically in the middle. Each one of these graphs is calibrated to the amount of population in the city. So if you go to the next one here, you've got this one here, and you've got, so for example, Houston, 100% penetration at 3.8 million people. That means you probably have at least 4 wells to store your gas. It's probably at least 1 or 2 service stations associated with each one of those storage wells for providing enough gas for it. I'm not sure how many people, Stan, how many people live in Hawaii? Is there in the island where you're living? Is that about 2 million?
Close to Pittsburgh. Yeah.
Okay.
We're less than that, but we're in the 1.3, 1.4 million right now, statewide.
So you guys could probably build, say, 2 100 megawatt geothermal power plants, and that would provide you with more than enough hydrogen to provide the transportation fuel for trucks and cars throughout all of Hawaii. And I'm not talking about just for fuel cells. There's an entire group right now. I think Ford and also Toyota are building internal combustion engines that burn hydrogen. So most all your transportation fuel and backup power for your power grid could be provided this way. The other aspect of it too, and this has to do with what's going on there in Hawaii, is that there is an ability, even with the geology that you do have there in Hawaii, right, that you could build synthetic gas storage there by by using horizontal drilling and fracking your basalt and using high brine content salt water to frack it with. And it really has to do with the reaction between the basalt and the brine itself. Now, here in the continental United States, understand we all live on an ocean of molten rock. Here in the continental United States, the crust where I'm at is about 30 kilometers thick. But there in Hawaii, all of you are blessed because the crust there in Hawaii is only 7 kilometers thick. I've got drill crews over here in Hawaii. These guys, for going at the Marcellus Shale, they drill down between 25 to 30,000 feet. You're talking about, 8-9 kilometers deep. So we've already got the drilling technology in the oil and gas business. We could drill completely through the crust there in Hawaii. And since I've already showed you, you don't have to drill deep enough to bring water to a boil. I just need to drill deep enough to bring the pentane to a boil. The only real risk when you're implementing this type of power source there in Hawaii is really the first well. And I think that's already been said before, that first well, that first pilot well, because you need to figure out the geology before you go to and actually convert over. Now, I know that there in Hawaii that AES owns, is it a coal-fired power plant, Stan? Is that correct? There in Hawaii that AES owns?
Yes, it was shut down last September.
Okay. Well, that's a prime candidate because all it requires to go in there, remove the smokestack, remove the scrubber, drill the wells, put in the heat exchangers. That's a primary, because you can build these anyway. You don't have to build it on a hopscotch because it's just a function of how deep you drill the wells to get at the temperature. So that power plant right there is a prime candidate for converted over to a geothermal power plant. Now, this here is a graphic from the Department of Energy. Now, it says EGS. It's called an enhanced geothermal system. I call it engineered geothermal system. That's where you drill multiple wells using horizontal drilling and fracking the rock. And according to the Department of Energy, more than 500 gigawatts of electric power could be produced by geothermal here in the United States. So that's a heck of a testament. And I've seen some estimates that go high as maybe a couple terawatts. The point being is this is a type of power source that could be deployed anywhere in the United States to produce electric power. The other advantage the geothermal power plant has over other types of power plants is you don't have to worry about fuel economy. When you're running coal, nuclear, gas, even biomass, you have to worry about how much fuel you're burning up. Well, in geothermal, you're tied into an infinite power source. So you can afford to run that power plant very inefficiently. What I mean by that is it's better to run a power plant at full power all the time. That way, the thermal stresses and everything is even on the plant. It actually helps keep the equipment from wearing out. What really wears out any type of machinery is ramping it up and down, trying to do load following. The advantage of running a power plant that way is no matter what the demand is on the grid, right? The excess energy you get out of that steam turbine, you can use that excess energy to turn it into hydrogen gas and then store it, underground in like a synthetic well. I think I'm available for questions. Oh, by the way, what you're seeing right there, that's a 110 megawatt steam turbine, like that technical diagram I was showing. So it's a piece of equipment. It's a lot smaller than what most people think it is for the amount of power it generates.
All right, Dan, thank you very much for a informative discussion, particularly on the technologies involved with geothermal and others. And for the group, these programs are recorded. Renew Rebuild should be posting the recordings, and you can go back and look at a lot of the data because you can freeze your screen and look at the data. So both Peter and Dan have given us a lot to look at, and it's all resourced there where you can see where the data came from. A lot of it's from Department of Energy, from financial institutions that we're used to dealing. And I've worked with both these gentlemen for years, and they track this stuff really closely with viable data. So for questions, Olivia, did you come up with any more questions from the group?
I believe pretty much all of the questions or most of the questions in chat were answered during or after the presentations, but if anyone has any more that they'd like to add, you're welcome to put them in the chat. And I think Gary Rosenberg.
Yeah, Gary has his hand up.
Like to say something?
Hey, thank all of you for great presentations. I just wanted to ask Dan, could you just extrapolate a little bit? I think it's fascinating that you start talking about we have the technology within the oil industry to convert to geothermal, giving the oil industry an opportunity to transition is very exciting. Can you talk a little bit about how you feel some of the potentially stranded assets in the oil industry might be converted to geothermal?
Well, how the oil and gas interests sell it. When you're talking about the drillers, the wildcatters, those are all small and medium businesses. They're not the Exxons and the Chevrons and those guys. The truth is, the big companies, really all they are is just financing because they've got access to Wall Street money. When it comes to the drillers, these are all just small business people. Most of the drillers I know, here in Indiana, we've got depleted oil and gas fields, and over in Ohio, you got the Marcellus shales, and these guys have literally drilled, thousands of wells drilling for shale gas. Over here, the average depth is between 25 to 28,000 feet. And it's not that unusual for them to accidentally, for when they're drilling and fracking one well, for the frack water to break out and come up out another well. And we've got water coming on the ground 300-400 degrees already, so that's with what we're doing right now. So there isn't really anything new that has to be invented. Probably the big thing that changed, I think a lot of people in this space thought that you had to have water hot enough to produce supercritical steam to drive a turbine. Well, the Raft River power plant that was built 40 years ago proved that that's not the case. You can use an alternative fuel, an alternative liquid to drive that turbine. That happens to be that isopentane. So between those, by taking the binary geothermal power plant, that isopentane, and our existing drilling technology, we already have the ability to drill, deep enough. Now, when I talk about over in Ohio, when you're talking about, 28,000 feet, that's 8 kilometers down. It's actually easier to build geothermal power plants in Hawaii because the crust where you're at is only 7 kilometers deep. That means we only need to drill about 6 kilometers. As
Hey,
far
Dan.
as go ahead.
Yeah, to get to Gary's point, when you have drillers, wildcat small businesses going bankrupt because you're not allowed to drill anymore, you could be using that specialty, that valuable human resource and the equipment to be doing geothermal wells instead of drilling oil wells. But if you let that valuable resource go idle, those people find different jobs, get into different careers, and now they're not available to drill wells. So doesn't it make more sense? I think what Gary's point was, doesn't it make more sense to have a plan to transition those wildcatters to drilling
Hey, Stan?
geothermal wells?
Sorry,
Yeah.
sorry to interrupt. If you Google TXGEA, Texas Geothermal Energy Association, there's a very, very sophisticated operation going on there where they're repurposing abandoned wellbores and using it for geothermal energy. So, there's a robust industry in Texas that is doing exactly what we're talking about, which is to repurpose these existing wellbores and develop geothermal energy.
To your point, Peter, that's what we're talking about here in Indiana, Ohio, Michigan, taking already existing wells. And in fact, one of the things we talked about, Peter, is over in the state of New York, up in Syracuse, the town of Syracuse, they had a bunch of depleted gas wells. And now the water isn't hot enough to drive a geothermal power plant, but the water coming out of their ground is more than, I think it's like 178 degrees Fahrenheit. Well, that's hot enough. They're taking that water and using it to heat up homes. So even with the existing wells, we're talking about converting existing wells like the Marcellus Shale over in Ohio, converting those over into geothermal power plants. But yeah, as far as like Baker Hughes and all those companies, that's something that everybody politically needs to push on, especially the folks here in DC, that, hey, we need to actually have a program to take the drillers and the rigs and repurpose them for doing geothermal. And whether you're doing geothermal power plants or whether you're using geothermal for heating homes, it's a heck of an energy source that we can't ignore.
So thanks for the question, Gary. And Olivia, are there any more questions out there that you picked up on?
A lot of comments. The only question that I see recently is, can these excellent presentations be downloaded from Andy? Yes, most likely, if I'm able to get them from the presenters. If you're subscribed to Renew Rebuild Hawaii, I'll probably send them out as an email after the fact if the presenters are okay with it.
Okay, and if this is being recorded, then
Yeah,
people
and also
could.
this entire conference will be posted on YouTube and on our website after the fact for you to be able to view.
Thanks, Olivia. I appreciate your help. So I'm going to turn it back over to Michael Markrich after I thank Dan and Peter and Stephen for their presentations, and really appreciate the quality and the information they presented to the folks in Hawaii. I hope it gives everyone here and even the folks listening in from Korea and from New Zealand a little bit more to think about in terms of geothermal. So Michael, over to you.
I want to thank you, all the presenters, for such an excellent work. And I want to thank our sponsors, Hawaiian Electric and the Hawaii State Energy Office, for helping make this possible. So until the next time, for Renew Rebuild Hawaii, aloha, and thank you.